Grignards. So here's a problem we looked at. This is an ester. This is a Grignard. This, for some reason, is a solvent. I would never choose to put it above the arrow like this. And I would also probably call it a solvent. So solvents, we don't want solvents involved with Grignards. Right? We always pick solvents that are obviously polar solvents, but we want them to be aprotic. So we don't want the solvent involved with the Grignard. If it's a protic solvent, that's going to react with the Grignard. So we don't want that. I know why they did that. But a Grignard, again, is a carbanion. So people ask about this. It's really like an ionic bond. So you could redraw this, if you want to, just like this, of the lone pair. And the magnesium is essentially along for the ride. It's just a balanced charge. Magnesium has nothing to do with the mechanism. So no arrows go to the magnesium, nothing. It's just there to balance charge. Okay? Only time we use the magnesium is when we generate the Grignard. That's that radical process. That's the only time we use the fishhook arrow so far, is to make the Grignard. Right? Because it's a metal, so we use a radical process for that. If I took one step back, what does that look like? So this came from like this. And we had magnesium that has 2 electrons. Right? It's a metal, so it's not very electronegative, so it's willing to give up those electrons. How many electrons are in a bond? 2. So we just made 2 new bonds. What we made was this, which of course behaves and reacts like this. Right? But you got to be used to seeing it those ways, those 2 different ways. All right, so Grignard reacts like this. We could draw it like this. Mechanism arrows. Oops. The broad one. That's cool. We're going to do that addition step. Right, we're going to do that addition step. My nucleophile is the carbon, this carbanion. This is my electrophile. Let's number some of these things. 1, 2, 3, 4, 5, 6. Which new bond did we form? We formed a new bond between C1 and C2. We broke a pi bond between C2 and O3. So let's back up again. Let's see what that product would be. This addition reaction. So here's the product of the addition. Let's make sure we number our carbons. So we said C1 was going to be bound to C2, and it broke the pi bond between C2 and O3. There's carbon 4, oxygen 5, carbon 6. What do we call this? We call this a tetrahedral intermediate. Why is it called the tetrahedral intermediate? Right? Why is it called that? It's called that because we went from sp2 hybridized to sp3. What's the geometry of sp3 hybridized? It's tetrahedral. So we have a tetrahedral intermediate. Once you have a tetrahedral intermediate, what do you ask yourself always? Do I have a good leaving group? Now, do you have a good leaving group? Some people have asked this. It's a good question. How do I know what's a good leaving group? Well, let's go back to thinking about how we stabilize like a negative charge. What are the things that help stabilize a negative charge? Electronegativity. Right? What stabilizes negative charge? Electronegativity. Is something electronegative? More electronegative things are happier with the charge. Larger things are happier with charges. Right? A big old iodide can spread the charge out. Resonance. Right? If a leaving group can do resonance, that stabilizes a negative charge. Is there anything else I'm missing that stabilizes negative charges? So things that are electronegative, size, bigger things can stabilize negative charge, bigger atoms, and resonance can help stabilize negative charges. Now, some people might say, well, wait a second. O- isn't that good of a leaving group. I remember hearing that. You're right, it's not that good of a leaving group. But let's take a step back and think about this. Would you rather have O- or C-? Which one's more stable, O- or C-? Which one's less reactive? O- is actually less reactive than C-, right? So the reason why this reaction goes right, is because you're actually making something more stable. Even though it's still pretty reactive, it's more stable than C minus, right? So we end up with an O minus. So because we have a good leaving group, that's electronegative, right? And we have an O minus, what we're going to do is we're going to do an elimination. We're going to reform that pi bond. So here's the product of elimination. This is a ketone. Notice how I numbered everything, right? We formed a new bond between 2 and 3, a new pi bond. I went back because even after I said it, I forgot it. Right? Where was the chart? I forgot the magnesium plus. Right? I forgot to put that in there. And right, it's still along the way. Right? It's just there to balance charge, though. It's not. There's no arrows going to it or anything. It's just there to balance the charge. Mg plus, MgBr plus. Right? It's just there to balance the charge. So we did an addition. Had tetrahedral intermediate. Do we have a good leaving group? Yes. We're going to do the elimination. What did we just make? Well, now we made a ketone. Right? And of course, we also have this leaving group, right? So we exchange one O minus for another O minus. Great. No difference. What do we know about ketones? Ketones are actually more reactive than esters. Why are ketones more reactive? Why is this carbon more reactive than esters? What can esters do that ketones can't? Esters can do resonance, right? Because this oxygen has lone pairs, it can do resonance. That makes this carbon less electron deficient, less delta plus. So we actually make an intermediate that's more reactive than the starting materials. So what's going to happen to this right away? It's going to react, right? So a lot of people have a question about why can't we stop at the ketone? We can't because it's too reactive. It's more reactive. This intermediate is more reactive than the starting materials. That's why this Grignard's in excess. So what's going to happen? We're going to have another Grignard react again. All right, ready for another Grignard to add? Because we have the more reactive ketone. The first step is going to be adding into the carbon of the carbonyl group. Do that addition reaction. What do we end up with? An O minus. The magnesium bromide is along for the ride. No arrow, don't worry about arrows to that. Number our carbons to make sure we didn't lose anything. There's 2, there's 3, number our atoms. There's 1, there's 7. Have I lost anything along the way? Hopefully not. We did an addition. We have a tetrahedral intermediate. What do we ask ourselves when we have a tetrahedral intermediate? Do we have a good leaving group? Do we have a good leaving group here? All we have is carbons, no good leaving groups. So if we don't have a good leaving group, what do? We go on to the next step, which finally is just protonation. All right? Just the protonation at this point. And that gives us the final product, alcohol. This tertiary alcohol.